Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 26. In this lecture, we'll discuss Fermat's principle and Huygens principle. These topics are covered in Chapter 35 of our textbook by Surway and Jouet. Let's start with Fermat's principle. Fermat's principle states that in going from point A to point B, a beam of light takes the path of least time. Fermat's principle is important because it can be used to derive the laws of reflection and refraction, both of which we've discussed in previous lectures. The details of those derivations are not important for us here, so I will provide only an outline of how these laws can be derived. If you wanted to use Fermat's principle to derive the law of reflection, you would proceed as follows. Imagine you have a light source at point A and a detector, like a human eye, at point B. Also imagine that you have two media. Medium 1 on top in pink could be air, for example, and medium 2 on the bottom could be glass or some reflective surface. A beam of light emanating from point A and reflecting from the surface can end up at point B. We want to know exactly what path that beam would take. Here, I'm demonstrating three possible paths that I'm labeling as path 1, path 2, path 3. Given coordinates or angles for each one of these lines, we could calculate the total distance for each path. And then knowing the speed of light in this medium, we could calculate the time required to travel each path. We would then find that the path that minimizes time, the path of least time, is path 2. That path happens to be the path that conforms to the law of reflection. Path 2 is exactly the path for which the angle of incidence is equal to the angle of reflection. If you wanted to use Fermat's principle to derive the law of refraction, you would proceed as follows. Once again, imagine a light source, and imagine that beams of light emanating from point A end up at point B. Also imagine two media. The first medium on top could be air, and the second medium on the bottom could be water, for example. A light beam emanating from point A would reach the boundary or the interface between the two media. It would bend or refract and eventually end up at point B. We want to know exactly what path that beam would follow. Here I'm demonstrating four possible paths that are labeled as paths 1, 2, 3, and 4. If we had coordinates or angles for each of these lines, we could once again calculate the total distance. Knowing the speeds in medium 1 and medium 2, we could then calculate the total time required for each path. And then we would find that the path of least time is not necessarily the most direct path, like path 2, but an indirect path, like path 3. We would find that a broken path, like path 3, is exactly the one that conforms to Snell's law or the law of refraction. In this context, it's important to recognize that the path of least time is not necessarily the path of least distance. In the case where the beams are all confined to one medium, least distance and least time are essentially the same thing. But when the beams travel from one medium into another medium and the speed changes, then least time is definitely not the same thing as least distance. You probably understand what this means if you've ever had to drive through traffic. The congested route on the highway, which might be the shortest path, is not necessarily the quickest path. Sometimes you choose to take a longer path home because although the distance is larger, the time is shorter. I should mention a few facts about Fermat. Pierre de Fermat was a French mathematician and lawyer. Today, he is most famous for two things. Firstly, Fermat's principle, which we were just discussing, and secondly, Fermat's last theorem. Fermat's last theorem is a theorem from mathematics which states that the equation a to the n plus b to the n equals c to the n, where n is greater than or equal to 3, does not have any integer solutions. In other words, there does not exist integers a, b, and c that can satisfy this equation when n is 3 or greater. When n is equal to 2, there does exist integer solutions. A, b, and c could equal to 3, 4, and 5, and the equation is satisfied. But if n is 3 or larger, then there are no integer solutions. Fermat claimed that he had found a proof to this theorem, but he claimed that the margins of the book in which he was writing were not large enough for him to include the proof there, and that he would provide it later. Fermat died and never provided the proof, and for a few hundred years, mathematicians wondered how Pierre de Fermat had managed to prove this very important theorem in mathematics. The theorem was finally proven in 1995 by the English mathematician Andrew Wiles. The techniques that Wiles used to prove the theorem were quite sophisticated and on the cutting edge. These techniques did not exist back in the 1600s, so it's quite doubtful that Fermat was actually able to prove this theorem. Nonetheless, the theorem is still often referred to as Fermat's last theorem. It turns out today we no longer view Fermat's principle as a rigorous principle. Today we use more rigorous proofs for the laws of reflection and refraction that are based on Maxwell's equations from electrodynamics. Nonetheless, it's good to mention Fermat because Fermat's principle motivated many other important ideas in physics. Fermat's principle later on motivated ideas related to the minimization of energy, maximization of entropy, and the optimization of action. So this idea that nature behaves in a way to minimize, maximize, or optimize a quantity like time or energy or entropy or action is an idea that has had long-lasting and important influence on modern physics. The next important character in our story is Christaan Huygens. Huygens' principle states that every point on a wave front generates new waves. The successive generation of new waves results in the propagation of energy. So Huygens imagined wave fronts as being essentially a combination or superposition of smaller waves, which today we call wavelets. So as a wave front propagates from its initial position to final position, we can imagine that it is being generated by a series of wavelets, each wavelet having its center on the original or the initial wavefront. So each one of these 3 points on the wavefront at one time generates spherical or circular wavelets, and then the combination or the superposition of those wavelets a few seconds later generates the wavefront at that time. This concept can also be applied to circular waves. Again, each point on the initial wavefront creates its own circular or spherical wavelets. When those wavelets combine a few seconds later, they create the new wavefront at that point. Huygens' principle, like Fermat's principle, is important because it can be used to derive the laws of reflection and refraction. However, Huygens' principle can go further. It can also explain the phenomena of interference and diffraction, which we will discuss later in our lectures. This animation demonstrates for us how Huygens must have imagined the reflection and refraction of light. In this animation, we see a single wavefront propagating towards the boundary between two media. You can imagine air on top of water, for example. We're interested in knowing how this wavefront reflects from this boundary and how it is transmitted and refracted in the second medium. To understand this, Huygens imagined that there is a series of point charges, like maybe the atoms or electrons, of the medium arranged along the boundary. As the wavefront arrives at each point charge, it exerts a force and causes that point charge to oscillate. As each point charge oscillates, it generates new waves. These waves are circular or spherical waves that simply emanate from that point charge. As you can see, the waves travel faster in the first medium and slower in the second medium. If we look at the superposition of many of these circular waves, we see that they form a coherent wavefront in medium 1 and a different one in medium 2. We can now draw a ray. Remember that the ray is always perpendicular to the wavefront. The ray basically indicates the direction in which energy must be traveling. As you can see, the reflected wavefront is perpendicular to the reflected ray, while the refracted wavefront is perpendicular to the refracted ray. Of course, in practice, there isn't just a single wavefront. There are many successive wavefronts that are incident on the boundary. As each wavefront arrives at the location of a point charge on the boundary, it activates that point charge. The charge begins to oscillate. The charge then generates its own wavelengths, and the superposition of those wavelets is ultimately what results in reflection and refraction. As you can see, it's a rather complicated situation on the microscopic level, but we can simplify this very complicated picture by looking at the wavefronts only. We can simplify it even further by looking at the rays. I should mention a few facts about Huygens. Christaan Huygens was a Dutch mathematician, physicist, and inventor. Today, Huygens is most famous for Huygens' Principle, which we were just discussing, but also for his discovery of Saturn's moon Titan and for his invention of the pendulum clock. Huygens was able to discover Titan through improvements that he had made to the optical telescope, and his invention of the pendulum clock truly revolutionized timekeeping for the next 3 centuries. Note that back in the 17th century, if you wanted to know what time it was, you would have to use a sundial. The best sundials can tell you the difference between 1 o'clock and 2 o'clock, but they cannot tell you the difference between 1 o'clock and 5 minutes past 1 o'clock. For measurements of time on the order of minutes and seconds, you would have to use an hourglass, which is horribly inaccurate, or you would probably use the human heartbeat. Of course, if you're going to use the heartbeat, then you have to make sure that your human clock is neither too excited nor too tired that day, because both of those things can affect the rate of the human heartbeat. So when Huygens invented the pendulum clock, he truly revolutionized science, because for the first time, scientists had a way of accurately measuring time on the order of seconds. I should also mention that Huygens' principle, like Fermat's principle, is no longer viewed as a truly rigorous proof for the laws of reflection and refraction. Today, we use more rigorous proofs based on Maxwell's equations from electrodynamics. Nonetheless, it's important to know about Huygens' principle because Huygens' principle established the wave theory of light, which was later used to explain phenomena like interference and diffraction. We'll discuss these phenomena later in the course. And that is the end of this lecture. Thank you for your attention.